Hello and welcome back. Today we're going to talk about a different discrete probability distribution. So we've gone over the binomial distribution, and if you recall, the binomial distribution, it was the number of successes per a set number of trials. And so if we flipped a coin 30 times, there's no way that we could get more than 30 heads or 30 tails. Now, obviously, we're going to be, at some point we might be dealing with some type of data where that's not going to be the case, where there's not a distinct number of trials and the number of outcomes or the number of observations might be constrained from 0 all the way to, in principle, infinity. And this is where the Poisson distribution comes into play. So the Poisson distribution, like the binomial distribution, is a discrete distribution. So each random variable drawn from that distribution is going to be an integer, and it's going to take on a discrete value. So there's either going to be 1, there's going to be 2, all the way up to infinity. And the Poisson is a really good distribution for relatively rare events. And what it will do is it'll give us the probability that we've observed a number of events during some fixed interval. So for example, perhaps the number of matings observed during a breeding season, or maybe the number of birds that are coming to your bird feeder per hour. Some fixed interval, some unit of time. That is what the Poisson distribution is built for. So that's different than a binomial distribution. If you were counting birds at your bird feeder per hour, you could in principle have anywhere between 0 and an infinite number of birds. Whereas the binomial distribution, there would be a fixed number of birds, and that's not going to apply to this type of situation. So Poisson distribution is good for modeling things that are countable and where there is not a fixed number of trials. Rather, you're looking at the number of observations over some fixed interval. And in other words, we're going to be thinking about things that we can think about the rate at which we're seeing something. And an interesting thing about that, it being a weight, another way that people think about the Poisson distribution is the waiting time for an event to occur. And so, for example, perhaps you're going to do an experiment where you have 1,000 washing machines and you're interested in knowing, on average, how many years does it take for a washing machine to fail? There, the thing that you would be counting is the number of years, and it would be the number of years per failure of a washing machine. In principle, a washing machine could function forever. It could last an infinite number of years. And so if you had a large sample of washing machines, you could just count the number of years it takes for it to fail, and that would be the data then that you'd be modeling. Likewise, you could take the number of years on average it takes for a seed to die in the seed bank. In principle, hypothetically speaking, a seed might persist in the seed bank for an infinite number of years. And so or it could be obviously less than that. And so what we'd be doing there is we'd be counting up the number of years for each seed to die, and then we could model that as a Poisson. And it doesn't really necessarily, it does matter, but it depends on your question. If your question is you want to know how many seed deaths do you expect per year, then the rate that we would be thinking about is seed deaths per year. If you want to think about the number of years on average per seed death, then it would be years over seed death. And so once we've decided how we're going to model it, we can go ahead and we can use the Poisson distribution. So fun fact, the first application of the Poisson distribution, or at least the earliest known application of the Poisson distribution, was actually done by the Prussian army, where they were modeling they were coming up with the expected number of deaths per year due to soldiers being kicked in the head by a horse. And so being kicked in the head and killed by a horse was a relatively rare occurrence, but it did happen. And what they wanted to do is they wanted to have an expected value. How many do I expect to die per year? Again, it's a rate. The rate would be deaths by getting kicked in the head by the horse per year. And once you have that rate, you can apply it to a Poisson distribution. And so, as I said, like the binomial distribution, the Poisson distribution is a discrete distribution. And unlike the binomial distribution, there's not a fixed number of trials. And so we could then take our data, our count data, something that we've counted, some kind of integer, and we can say that it is distributed as a Poisson distribution. And so it would look something like this. So y is distributed as a Poisson with parameter lambda. So remember when we did a binomial, the parameters of interest were the probability of an event occurring, but we also had to include the number of trials. Here, all we have is a rate. And so this rate, again, could be number of birds at your feeder per hour. So if you saw 5 birds in 1 hour, then you would turn that into a rate and you would put that in as lambda. Like the binomial distribution, the Poisson distribution is going to be described formally by a probability mass function. And this will tell us the probability of observing y, which again is going to be an integer somewhere between 0 and infinity, given our estimate of the rate, which is lambda. And it's simply lambda to the y over the factorial of y multiplied by Euler's constant, so the base of the natural log raised to the negative lambda power. Now, when we did the binomial, we went through and we built that probability mass function from the ground up to take some of the magic out of it, and it's a pretty simple distribution, and we can kind of understand what those distributions are. We do not need to memorize that. There's no reason to memorize that because we can always just go onto Wikipedia and find out what the probability. So here, look at that. Look at how smart I am. I know how to use Wikipedia. So I just did a Google search. There's the Poisson distribution, and lo and behold, right there is our probability mass function. So there's no reason to memorize this because it's always going to be in a book. What we need to know is how to use it. And so let me get my face back on here for just a second. And so let's play around a little bit with the Poisson distribution. And the first thing we can do is we can look at how the shape of that distribution changes as we change lambda. And so I'm going to just run a little bit of code here that we can look at. Oh, of course it is. Quartz. Now I will run that and feel good about myself. Okay, so here is the probability mass function of a Poisson. So this is at a lambda of 0.3. So the rate would be, maybe on average 0.3 birds per hour or whatever it might be. And then as we increase lambda, you'll see that it starts to actually resemble what the binomial function looked like. And if we were to make a very large lambda, very, very large lambda, the Poisson would essentially converge on the same shape as a binomial. But I just wanted to point out that as you increase lambda, which is the rate of something occurring, that the shape changes. So here, if we have a lambda of 4.3, you can see that most of this probability mass is around 4. And likewise, if we go way over here, lambda at 0.3, most of that probability mass is around 0. Okay, so it's the shape of lambda, much like with the binomial distribution, the shape of the probability mass function for the Poisson will change as we change that parameter lambda. And so let's see here. I'm going to put myself in the little corner here in case I get excited and I want to show how excited I am. So how can we use this? Well, first of all, if we go back to the probability mass function, the first thing that we would want to do is we have our data and we want to come up with some kind of an estimate for lambda. Like, where is that lambda thing coming from? And just like we did with the binomial, we could take this probability mass function, we could take the first derivative of it, and we could solve for where the slope is equal to 0. And if we were to do that, which we're not going to do, but if we were to do that, what we would find is that lambda is estimated as the arithmetic mean of all of your observations. So if you're counting birds and you're recording the number of birds that are coming to your feeder per hour, and you do that for 10 hours over 10 days, however you decide to set up your experiment, you would have 10 observations of the number of birds per hour, and you would simply divide that by 10, and that would give you the rate. That would give you the average number of birds you expect per hour, and that's what this parameter lambda is telling us. And so we've already gone pretty in depth into thinking about how to use the binomial distribution, and once we know how to use a distribution, all of these other distributions, as long as we understand what all other distributions are doing, the same rules are going to apply. And so let's take a hypothetical example where, let's say that we've been working in the Smoky Mountains for quite a while, and we have some estimate of the density of bears. And so let's go ahead, and I will draw that up here, and I will paste it from the script. So let's say that the average number of male bears per hectare is 0.3, which means on average, if you go to, what that means is that would have been estimated by going out to various hectare plots and counting the number of bears you saw. And so maybe you went to a bunch of different hectares and you counted the number of bears. There were lots of hectares that had no bears in them. Some of them had 1 bear, some of them might have even had 2 or 3 bears. And we take all of those observations and we average it, and we come up with 0.3. And so this is our rate parameter. This is the parameter that we will put into a Poisson distribution. And so once we have that, we can calculate the probability of any given type of observation. So let's say we wanted to know the probability of there being 4 bears in any randomly sampled hectare. Well, since we want to know the probability of there being 4 bears, we can use a function called d Poisson. And d Poisson will be the probability mass function for a Poisson. And what we need to put in there then is simply, what is the probability, say that there are 4 bears, we would say d Poisson 4, and lambda, I will be explicit, lambda equals 0.3. And so that is the probability that I would go to any randomly selected hectare and I would see 4 bears in that hectare. That's a lot of male bears to have in a hectare, and it's a really low probability that I would see that. We could similarly have calculated that by doing the probability oh no, I can't get out of the way. By doing the probability mass function for the Poisson distribution. So if I go ahead and I pop that in, I get the exact same answer. And so all the d Poisson function is doing is it's calling up the probability mass function for a Poisson. And so also, just like with the binomial, we have what's called a cumulative probability distribution, which again is going to say the first value is going to be the probability of there being 0 bears, and then the next one will be the probability of there being 0 or 1 bears, so on and so forth. Said it again. And we can look at what that might look like for these data that we're playing with for our hypothetical situation. And what I'm going to do is I'm going to create an object called p.x.bears, and basically all I'm doing is I'm looking at the probability mass of there being somewhere between 0 and 20 bears per hectare, where there's always the rate at which you expect to see bears is 0.3 bears per hectare. So if I were to just run that, this right here is the probability that there would be 0 bears. And so 74% of the time you would expect, for any randomly selected hectare, 74% of the time you expect to see 0 bears. And then here, 22% of the time you expect to see one bear. And now it gets down to 3% of the time you expect to see one bear. Or I'm sorry, 3% of the time you expect to see two bears. And then 0.3% of the time you expect to see four bears, and so on and so forth, all the way up to this is the probability that you would see 20 bears. Again, just like the binomial, there's 21 possibilities out of 20 with the 20, because there's a chance you'll see 0 bears as well as a chance that you'll see 20 bears. So I will go ahead and I will create this object called px bears, and it's going to be that vector. And then I can plot what the probability mass function looks like for our particular scenario. So I'm going to say quartz, and then I will plot it, is what I will do. Okay, so here is our probability mass function. So it's most probable that we're going to see 0 bears, and then here's the probability we'll see 1 bear, here's the probability we'll see 2 bears, and then really quickly, here's the probability we'll see 3 bears, and then really quickly it gets super close to 0. It is incredibly unlikely that you would see 20 bears in that forest. Yeah, that's the probability right there that you would see 20 bears, so not very probable. And then we can also think about what the cumulative distribution function might look like for that. So this again is the same information, just plotted in a different way. So this is the probability of there being 0 bears, which was 75-ish%. And then this would be the probability of there being either 0 or 1. And so this is simply this plus that, right? This is the probability mass function, and that is the cumulative distribution function. And so we can interpret these things the same way that we interpret the results from a binomial distribution. It's just that the Poisson is modeling something a little different. The data kind of looks similar because we're counting things, but again, there is no maximum number of observations we could have. In principle, we could observe 1 billion bears per hectare. The probability of that would be probably pretty darn close to 0, but we could do it if we wanted to. And so thinking about how we could do that, we can use our Poisson function. So we've already got the probability of there being 4 bears, let's say. We could ask, what's the probability that a sampled hectare would have 1 or fewer bears? And so there's 2 ways we could do that. We could first pull up Poisson, Poisson, and we could ask 0 or 1 bears. So we'll give it 0 or 1 bears, and lambda is 0.3. So those 2 numbers, right? This is the probability it's in 0. This is the probability it's in 1. And so if I take the sum of that, that's going to give me the probability that any given random patch I would go to, or hectare I would go to, that's the probability that I'll see 1 or fewer bears. We could do it also using the Poisson function, which we would use just like the binom function, except here it's Poisson, and we would get the exact same answer. And again, as I said with the binomial, get in the habit of answering those types of questions using the cumulative distribution function, because when we get to continuous distributions, doing this and taking the sum will be impossible. It's only possible because we're dealing with a discrete distribution. And so that means that if I wanted to know, well, what's the probability if I went, let's say I went out into the Smokies, and I wanted to know what is the probability that I would see more than 1 bear. And so there's 2 ways that I could do that. I could either take 1 minus the probability of seeing 0 or 1 or fewer bears, or I could say P Poisson 1 0.3 lower dot tail equals false. And it's going to give me the same answer. And so since there's an indeterminate number of observations, it wouldn't be possible to use, you could say 1 minus the sum of the d-Poisson. That would give us the same thing. But obviously there would be no way to just take the sum of d-Poisson from 0 to infinity. That's not possible to do, because then you would end up with a vector that's infinitely long, and that would be a problem. And so just in general, let's stay with the habit of using the Poisson function. Okay. And so let's take another example. Let's think about, let's say that you were looking at flowers, because who doesn't like to look at flowers, and you were counting the average, and you have calculated the average number of pollinator visits to a particular flower. And you've done that across a bunch of similar flowers, so you have a whole vector of the number of pollinators that you saw visit that flower in a minute. And let's say you took the average, the arithmetic mean of all that, and you end up with a rate of visitation of 0.7 pollinators per visit. And so we could ask, you know, what is the probability of, say, observing, let's see here, I'll put that, average number of pollinator visits is that. And so I could ask, for example, what is the probability of observing 4 or more visits in a minute? So based upon our data, and based upon the type of data, we're counting the number of pollinators. There's not a fixed number, there's not a maximum, so we know that the binomial probably isn't appropriate. And we've calculated this parameter lambda, and we've chosen to model it as a Poisson distribution. So if I want to know what is the probability of observing 4 or more visits in a minute, I could either take, the Poisson, the Poisson, the cumulative distribution function. And if I'm interested in what is the probability of observing 4 or more, what I want to do is I want to figure out what is the probability of observing 3 or less, and subtracting that value from 1, and then that will tell us the probability of having 4 or more. And so I'm going to ask, what's the probability of getting from 0 to 3 with a rate parameter of 0.7? And I would take that value and subtract it from 1. So a pretty low chance that I'm going to see 4 or more. The other way we could have done the same thing is to just simply say lower dot tail equals false. And it's going to give us the same number. And so we can use this, or we can use these functions in the same way, playing all the same games with using these functions that we did with binomial, except here we're dealing with a Poisson. One other thing I wanted to mention. It's really tempting to look at this rate parameter here on its own and think about what the expected observation should be. So if I were to ask, what do you expect to see whenever you go and you look at this bird feeder? Do you expect to see 0 birds? Do you expect to see 1? Do you expect to see 2? What is the most probable number of birds that you're going to see in any given moment? And it's very tempting to simply round the rate and say, well, 0.7, I guess I would expect to see 1. Like, that's the most likely number of birds that I would see. However, if we were to make myself small, if we were to look at the probabilities, this is the probability of seeing 0, this is the probability of seeing 1. So it's actually, even though the rate parameter is 0.7, it's more likely that you're going to see 0 individuals than you're going to see 1 individual. And so I just wanted to point that out, because a lot of times that throws off people, because they assume that if I was to come up with some expectation, you can simply just round the rate parameter to the closest integer, and that will give you the expected number that you should see. But that's not going to always be the case. So what you will need to do, if you are asked, well, how many do I expect to see based upon that parameter estimate of 0.7, you're going to have to explore the probability mass function and find out what value actually has the maximum value. And in this case, it's going to be 0. So that's the most common thing that you're going to see. A close second is going to see 1 pollinator, and then progressively it'll become less and less probable that, for example, here that you would see 5, or I guess that would be 4. What's the probability you would see 4? 4.9 times 10 to the negative third. Not very probable. Okay, I just wanted to point that out because sometimes that throws people, like, how do I know what the expected number is? And the expected number, you're going to have to use the probability mass function. Okay, back to the regularly scheduled programming. And so as a last exercise, because this one actually has maybe some applications to people, is this. Let's see here. And so what is the probability that a 100-year flood will occur at least once over a 30-year period? And normally I do this as an in-class exercise, so go ahead and if you're feeling it, go ahead and hit pause and try to answer this question about what is the probability that a 100-year flood will occur at least once over a 30-year period. So the first thing that we need to do is estimate lambda. And so again, a 100-year flood is a flood that we expect on average to occur once every 100 years. So we know that the big rate is one every 100 years. And then what we need to do is we need to estimate lambda. So we would do that by doing the arithmetic. We'd say 1 out of 100 is equal to what? Is equal to lambda over 30. Because what we're going to want is we're going to want it to be in units of floods per 30-year period, as opposed to floods per, or the expected number of floods over a 30-year period, given that we are already expecting 1 out of 100. And so the rate, again, the rate at which we're thinking about things, we just do a little bit of arithmetic, and we take that times 30. And so our rate parameter is 0.3. And so if we expect, per year, there's a 1 in 100 chance. Per 30 years, there's a 0.3 chance. And so what we've done is we've estimated our lambda. And let's go ahead and we can even assign it to an object called lambda. Okay, and so now we have our rate parameter. That is the number of 100-year floods per 30 years. And so we have 0.3. So we could use, and if the question is what is the probability that you will have at least 100-year flood occurring over a 30-year period, we could use the cumulative distribution function of a Poisson. And what we could say is, well, if we want at least 1, let's go ahead and use the pitfalls. So we'll take the cumulative distribution of having 0 or fewer, which obviously is just 0 in this case. Put our rate parameter in there, which I'll go ahead and lambda. We created the object, we might as well use it. And then lower dot tail equals false. And so this will give us the probability of there being 1 flood a year, or 1 flood over 30 years, 2 floods over 30 years, all the way up to an infinite number of floods per year. And so that is the probability that a 100-year flood will occur once over a 30-year period of time. Now, an alternate way to model this is you could model it as a binomial, right? Because there's 30 years to think about. And so we could say P binom, and I want to know the probability. Again, we're going to do probability of there being 0, because then we'll subtract, we'll take the other part of the probability mass over a 30-year period. So there's 30 trials. And the probability for any given year is 0.01. That's our probability. And then, of course, we will also say lower tail equals false. And you'll see that the binomial has a slightly different answer compared to the Poisson. And that's because it's a different distribution, first and foremost. But let's think about what they're doing differently. Both of them are, well, nothing is, that's not true either. There is not necessarily one correct way to do anything. There's plenty of wrong ways. I almost said there's no wrong way to do something, but there's clearly wrong ways to do something. But this is all about how we've chosen to model our data. The model that's probably better is the Poisson model. And why is that? The reason is because with a binomial model, we're only allowing there to be one 100-year flood per year. And I don't know if you remember, a couple of years ago, there was actually situations where we had multiple 100-year floods at the same location in the same year. The binomial will not allow us to have multiple floods in a given year, whereas a Poisson, there is a probability that there's going to be 0 floods, but then there's also a probability that there's going to be 1 flood, that there's going to be 2 floods, that there's going to be 3 floods. And so this is probably the better estimate for what your expectation is that you're going to have a 100-year flood over a 30-year period. And the reason why I chose over a 30-year period is because, you know, that's the average amount of time that a typical mortgage has, right? You buy a house and you're probably going to pay off a 30-year, you're going to try to pay off a 30-year mortgage. If you're in a flood zone, it's somewhat misleading to think like, oh, well, it's a 100-year flood. There's a 1 in 100 chance. I'm not going to live to be 100 years. That's not a big deal. But then when you actually think about what the probability is that you might actually experience a 100-year flood before you even pay off your mortgage, it's actually roughly a 25% chance. So when you think about it that way, then it's probably a really good idea to make sure that you have good flood insurance, because 25% chance is pretty good. Okay. That's it for the Poisson. I mean, again, once you understand how to use a discrete distribution, you can pop into the probability mass function or the cumulative distribution function and come up with some expectation about what future samples should look like or what the expected value is. And it's not really that different. The important difference is understanding that that binomial and Poisson are doing different things. And as long as you understand what the distribution is doing and you understand what the parameters are describing, you can explore a bunch of different types of discrete distributions. So the only discrete distributions that we're playing with in this class, at least up to this point, are the binomial and the Poisson. But who knows? There's actually a bunch of different discrete distributions. Multinomial, geometric, negative binomial. There's all kinds of them. So yeah, lots of different ones to choose from. The two most commonly used are the binomial and the Poisson. And so those are the two that I decided to introduce. But again, once you understand how to use probability mass function and a probability or a cumulative distribution function, all you have to do is find the appropriate distribution to use, and you can pop it into that mass function or that cumulative function. And that's it. And so enjoy yourself playing around with a little bit of Poisson, a little bit of binomial, and think carefully about imagining situations where binomial is appropriate for this type of a situation, a Poisson is more appropriate for this type of a situation. And then once you have that, you're golden, and you're ready to start playing with distributions. And so this will end our exploration of discrete distributions. We will come back to both of these discrete distributions at the very, very end of the semester, when we're building models that will use these distributions instead of the familiar normal distribution, which is what we tend to use for a lot of things. So on that, enjoy, and we'll see you next time when we decide that it's time for us to think about continuous distributions. It'll be exciting. I'm emoting. I'm excited. See ya.